It's amazing when you stop and think about it, isn't it? How we take just a chunk of ordinary rock and turn it into the gleaming metal that builds our cities, powers our phones, everything, really.
It absolutely is. It's this fundamental magic we rely on every single day, but rarely give a second thought.
Exactly. So today, we're diving deep into that, into the fascinating, really complex world of mineral processing. We're going to explore how raw ores get transformed into pure metals. It's a journey that's, well, ancient in some ways, but also incredibly high-tech. And for this journey, we're leaning on a really great chapter from Mining and the Environment by Dr. Karl-Heinz Spitz and John Trudner. It maps out that whole path, or to product, our mission, to unpack these intricate steps, maybe uncover some surprising bits of history, and definitely tackle the big environmental questions, giving you a real shortcut to understanding this vital industry.
And what's so striking, I think, is how these processes are often built right alongside the mines themselves. They have to be incredibly clever, designed specifically to pull out valuable minerals from ores where, honestly, the metals are almost never just sitting there pure.
Right.
Gold is maybe the famous exception. You might find a nugget. But most metals, they're locked up tight in mineral compounds. They need coaxing out, chemically speaking.
Okay, so let's unpack that coaxing process. The oldest trick in the book seems to be fire, right? Pyrometallurgy. It's ancient, predates history, but it's still the main way we do it today. Why is that? Why stick with fire?
That's a great point. And the reasons are pretty compelling, actually. First off, high temperatures make chemical reactions happen much faster. Speed means efficiency. Plus, when metals are molten, they're just easier to handle, easier to mix into alloys. Think casting shapes or blending metals.
Okay, like pouring liquid metal.
Exactly. And the other key thing, the ingredients you add, the fluxes, they're generally really cheap materials. Wow. So you've got speed, ease of handling, and low cost. That's a powerful combination. Copper smelting is probably the classic example of pyrometallurgy in action.
Right, copper. So walk us through that fiery journey. I understand it takes a specific kind of ore. You can't just smelt any old rock containing copper.
No, not economically anyway. You really need high-grade sulfide ores, things like chalcopyrite. And the reason is energy. These processes are incredibly energy hungry.
Okay.
But the core idea is you melt it all down, and the heavier molten copper or copper compounds separate naturally from the lighter molten waste materials. That's the slag.
Like oil and water, but much hotter.
Precisely. Molten rock and metal. And what comes out isn't pure copper right away. It goes through stages. You start with something called matte and gradually refine it.
Refining, so removing the unwanted stuff.
Exactly. Step by step. Impurities like iron and sulfur, which are just naturally in the ore, get removed. The iron usually ends up in that slag layer we mentioned. The sulfur, it turns into sulfur dioxide.
Yeah, so too. The stuff that smells like burnt matches.
That's the one. But here's the clever part in modern smelters, that SO2 isn't just vented anymore. It's captured, very efficiently actually, and it's turned into sulfuric acid, which is a really valuable industrial chemical. So you turn a potential pollutant into a product.
That's smart. Cleaner and more economical. But before you even get to the main furnace, I bet there's some important prep work involved. Getting the raw material just right. I read about something called a bedding system. What's that?
Oh, absolutely crucial. Preparation is key. That bedding system is basically a large-scale blending operation. See, the copper concentrates arrive from different mines, maybe even different countries, and their composition can vary quite a bit.
Ah, so you need consistency.
Precisely. The bedding system blends all these different feeds to create a uniform raw material for the smelter. This is vital for smooth, predictable operation. It avoids hiccups, helps control the chemistry, and importantly, makes the whole thing more economic. It even allows smelters to carefully manage tricky elements like arsenic or bismuth if they're present in some ores.
Makes sense. Blend out the variations. And what about water? I hear moisture is a big no-no in modern smelting.
It really is. Those raw concentrates can be quite damp, maybe 6%, sometimes even up to 14% moisture.
Wow.
But modern smelting furnaces, they need that material to be very dry. Less than 0.5% moisture.
Why such a big difference?
Several reasons. Drying cuts down the energy needed in the main furnace dramatically. Less water to evaporate, right? It also reduces the sheer volume of exhaust gases you need to handle and treat, which means smaller equipment and lower costs.
Yeah.
And it helps minimize unwanted emissions.
Okay.
Plus, keeping water out prevents the sulfur dioxide gas from getting diluted, which makes it easier and more efficient to capture for that sulfuric acid production.
And how do they dry it?
Increasingly, they use steam dryers. These are much more energy efficient and environmentally friendly compared to older methods that might use direct heating with, say, natural gas.
Interesting. Now, sometimes there's another step before smelting called roasting. What's that about? Is it always needed?
Roasting is an optional pre-treatment step. You heat the concentrate, but not as hot as smelting, think 500 to 700 degrees Celsius, and you do it with air present.
Okay, what does that achieve?
It converts some of the metal sulfides and drives off some of the sulfur as SO2 gas before it hits the main smelter. The solid stuff left over is called calcine. It basically pre-processes the ore.
And is that just for copper?
Mostly for copper, but interestingly, some gold ores get roasted too, especially ores where tiny gold particles are locked inside sulfide minerals like pyrite. Roasting helps break down the sulfides and liberates the gold, making it easier to extract later using cyanide.
Okay. So assuming you have your dried concentrate or your calcine, then comes the main event, the smelting furnace. What happens inside that fiery beast?
The prepared material goes into the furnace, heated to over 1200 degrees Celsius. That's incredibly hot.
Definitely.
Along with the concentrate, you add fluxes, typically silica, maybe limestone. At those temperatures, the unwanted impurities in the ore react with these fluxes. They combine to form that liquid slag we talked about. And because the slag is less dense, it floats right on top of the heavier molten metal layer.
Like cream on milk.
A very hot version, yes. And it's relatively easy to tap off or skim off that slag layer, removing the bulk of the impurities.
So what's left underneath?
What's left is primarily a mixture of copper sulfides and some iron sulfides. This molten mixture is called matte.
Matte. Okay, so still not pure copper.
Not yet.
Yeah.
That matte is the first main product from the smelting furnace itself.
So from matte, how do you get closer to pure copper?
The next stage is called converting. You take that liquid matte, transfer it to another vessel, and essentially blow air through it. The oxygen in the air reacts with the remaining sulfur and iron. The iron forms a slag, which is removed, and the sulfur goes off as more SO2 gas again, captured for acid production.
And what's left after converting?
What's left is called blister copper. It gets that name because as the last bits of SO2 escape the solidifying metal, they form little bubbles or blisters on the surface.
Blister copper, and how pure is that?
It's actually remarkably pure, already typically over 99% copper. Quite impressive.
Wow.
But for most uses, especially electrical wiring, even that's not quite pure enough. So there's usually one more fire refining step.
Another furnace?
Yep, in what's called an anode furnace. Here, they carefully adjust the oxygen level to remove the last traces of sulfur and other remaining impurities, casting the copper into specific shapes called anodes.
Anodes. Okay, that sounds like it's leading somewhere specific.
It absolutely is. It's leading to the final purification step, electrorefining. And this is where the process gets really precise.
Electrorefining, using electricity.
Exactly. It's quite ingenious, actually. Even the best chemical or fire-based methods struggle to get those last fractions of percent of impurities out. But electrorefining, it can achieve 99.99% pure copper, and it does it on a massive industrial scale.
99.99%. How does that work?
Okay, so you take those copper anodes, the slightly less pure copper from the fire refining stage, and you hang them in tanks filled with an electrolyte solution. It's basically copper sulfate and sulfuric acid in water.
Right.
In between the anodes, you hang thin starter sheets of pure copper. These are the cathodes.
Anodes and cathodes, like in a battery.
Similar principle. You apply a carefully controlled DC electric current. What happens is the copper from the impure anode dissolves into the electrolyte solution. But, and here's the clever bit, only the pure copper ions travel through the solution and deposit onto the pure cathode sheets.
So the impurities get left behind.
They do. They either stay dissolved in the electrolyte, or, crucially, they fall to the bottom of the tank as a kind of sludge. Meanwhile, the pure copper cathodes grow thicker and thicker over several days.
And these become the final product.
Yes, each cathode grows into a solid slab of incredibly pure copper, often weighing 100, maybe 150 kilograms, ready for market.
That's amazing. But you mentioned sludge at the bottom of the tank. Impurities falling out. Is that just waste?
Now that sludge is one of the most fascinating parts of the whole process. It's called anode slime.
Anode slime. Doesn't sound very valuable.
Oh, but it is. Because guess what else is often present in copper ores in tiny amounts?
Other metals.
Exactly. Gold, silver, platinum group metals. Even things like selenium and tellurium. These valuable metals don't dissolve in the electrolyte during electrorefining.
So they end up in the slime.
They concentrate in the anode slime. That slime is carefully collected and sent off to specialized precious metal refineries. It's like a hidden treasure chest, a concentrated byproduct stream full of valuable metals recovered from the copper refining process. A sort of unexpected Fort Knox, you could say.
Wow, so refining copper actually helps recover gold and silver too. That's incredible. Okay, so these fiery processes are clearly powerful, but it's also clear they come with significant environmental considerations. Let's shift focus to that, the emissions, gas, solid, liquid.
Absolutely. Pyrometallurgy inherently generates emissions, and managing them responsibly is a huge part of modern smelting. It's a constant focus.
Let's start with the air. We mentioned sulfur dioxide, SO2. Smelters produce huge amounts, right? Sometimes more SO2 than copper.
That's historically been true, yes.
Yeah.
And for a long time, it was often just released directly into the atmosphere through tall stacks. Think of places like Mount Isa in Australia, which did that up until 1999.
But that practice has largely stopped.
Oh, yes. The environmental pressure and regulations became immense, plus the technology to capture SO2 improved dramatically. Now, modern smelters capture well over 99% of the sulfur dioxide.
And turn it into sulfuric acid, as you said.
Exactly. Which addresses a major air pollution issue and creates a saleable product. It's a win-win, really.
But the legacy of those past emissions lingers, doesn't it? Acid rain, for example.
It does. The historical impact of SO2 emissions is undeniable. Acid rain caused significant documented damage. You mentioned the Black Forest in Germany earlier, and reduced maple syrup harvests in Quebec. Those were real, widely felt consequences. It led to some very emotional public debates and ultimately forced industries and governments worldwide to adopt much stricter SO2 emission standards. It really highlighted how industrial activity links into global environmental cycles.
Beyond SO2, what about dust? Those tiny particles getting into the air?
Particulate matter, yes.
Yeah.
That's another key focus. Smelters use sophisticated equipment to capture dust from the exhaust gases before they're released.
Like what kind of equipment?
Two main technologies are common. One is electrostatic precipitators, or ESPs. They work a bit like some home air purifiers, using an electrical charge to make dust particles stick to collecting plates.
Okay.
The other is called a baghouse. Think of it as a giant industrial-scale vacuum cleaner with huge fabric filters bags that trap the dust particles.
And what happens to all that collected dust?
Good question. In most cases, it's actually recycled right back into the smelting process. It still contains valuable metals, so recycling it recovers more product and minimizes waste.
Okay, that covers gases and dust. What about solid waste? Slag is the big one, right?
By volume, yes, slag is usually the largest solid waste stream from smelting. Remember, it's formed when those impurities in the ore combine with the fluxes.
What happens to it? Just dumped somewhere?
Increasingly, no. Modern practice often involves quenching the molten slag very rapidly with water. This shatters it into small, glassy granules.
Why glassy? What's the benefit?
The rapid cooling creates an amorphous, non-crystalline structure. What's really important is that this glassy matrix tends to lock up any trace metals within the slag, making them much less likely to leach out into the environment over time. It immobilizes them.
That's interesting. So can this granulated slag be used for anything?
Potentially, yes. And this is where things get really interesting regarding perceptions of waste. Our source material mentions case 7.4, highlighting a fascinating contrast. In some places, like Indonesia, granulated copper slag is still classified as hazardous waste, limiting its reuse.
But not everywhere.
No. In Sweden, for example, they've been using granulated slag, which they call iron sand, for over 30 years in road construction and as fill for industrial land.
Really? For roads?
Yes. Apparently, it has excellent properties, good insulation, good drainage. They've built hundreds of kilometers of roads and large land areas with it. It shows that with proper testing and understanding, what one place calls waste, another can see as a valuable resource.
That's a huge difference in approach. It really highlights the barrier that assumed risk or just perception can create.
It does, and it points towards the potential for a more circular economy if we evaluate materials based on their actual properties, not just their origin.
Are newer smelting technologies designed to produce less waste overall?
Absolutely. Technologies like the Mitsubishi continuous smelting process, mentioned in case 7.5, are designed from the ground up with waste minimization in mind. They have very sophisticated internal recycling loops. The goal is to keep reprocessing intermediate streams within the plant, recovering as much metal as possible, and ultimately producing very little final hazardous solid waste. It's a much more integrated closed-loop philosophy.
Okay, one last waste stream. Liquids. What kind of liquid wastes are there and how are they handled?
The main liquid wastes are usually things like wash water, used for cleaning equipment, and the effluent that comes from gas scrubbers the systems use to clean the exhaust gases.
Is the water just discharged?
No, much of it is recycled within the plant. Water is a valuable resource, especially in mining regions. However, you can't recycle indefinitely because dissolved salts and other compounds build up. So a certain amount, called a bleed-off stream, usually needs to be treated before it can be discharged or disposed of.
And how is it treated?
Treatment depends on what's in the water. If it's highly acidic, it's typically neutralized, often by adding lime, which produces gypsum sludge. If the wastewater contains dissolved metals, copper, lead, zinc, maybe arsenic-specific chemical treatments are used to precipitate those metals out of the solution. This forms a concentrated heavy metals cake.
And that cake.
It can often be recycled back into the smelter to recover the metals, or if that's not feasible, it's disposed of as a controlled waste.
Okay, that gives us a good picture of the environmental management around pyrometallurgy. Now let's pivot completely. Let's talk about a different approach. Hydrometallurgy, using liquids, chemistry, not fire. And this is where gold processing really comes into its own.
Exactly. Hydrometallurgy literally means water-based metallurgy. The core process here is leaching.
Leaching? Like making tea, dissolving the good stuff out.
That's a perfect analogy. You're using a chemical solution, a lixiviant, to selectively dissolve the desired metal out of the ore, leaving the unwanted rock, the gangue, behind. Just like hot water dissolves the flavor from tea leaves.
And for gold, the go-to method for a long time involved physical separation or maybe mercury.
Yes, for coarser gold particles, physical methods like panning or sluicing worked. And mercury amalgamation was used for centuries. Mercury forms an alloy with gold, helping to separate it.
But that changed.
It did, significantly. By the 1980s, particularly in South Africa where mines were going deeper, the ores became more complex. They had more sulfide minerals, and the gold particles were often much finer, sometimes microscopic. Mercury just wasn't efficient anymore for these types of ores.
So what took over?
Cyanide leaching. It was introduced around 1890, actually, but became dominant for these challenging ores later on. It proved to be a vast improvement, much more effective at dissolving those very fine disseminated gold particles. Today, it's the primary method worldwide.
Okay, but cyanide, that word carries a lot of baggage, doesn't it? Why cyanide, specifically?
It does have a fearsome reputation, and that's understandable given its toxicity at high concentrations. But here's the crucial chemical reason. Cyanide is one of the very few substances that can effectively dissolve gold in water, using only the oxygen naturally present in the air.
Just oxygen from the air.
Yes. Other chemicals that could dissolve gold would require adding much stronger, more hazardous oxidants, think chlorine gas or strong acids. That makes them far less practical, more dangerous, and more expensive for large-scale mining. Cyanide, used carefully, is surprisingly effective and relatively simple chemically for this specific job.
So how is that risk managed in practice? You said it's toxic at high concentrations. What about at the mine?
That's the key point. At the mine, it's used in very dilute solutions, typically only 0.01% to 0.05% cyanide in water. That's 100 to 500 parts per million. And its use is incredibly tightly controlled. Regulations require secondary containment for all tanks and pipelines, automatic leak detection, extensive employee training on safe handling procedures, and strict protocols for transport, storage, and eventual detoxification or disposal.
So multiple layers of safety.
Absolutely. And this rigorous management is why, despite its inherent toxicity, the industry has used it for over a century without, according to the sources, recorded human fatalities directly linked to its process use in mining.
Okay. And you mentioned different types of cyanide earlier when we discussed regulations. Wad cyanide versus total cyanide.
Right, that's an important technical distinction for understanding risk and regulation. Weak acid dissociable, or WAD cyanide, refers to the forms of cyanide like free cyanide and some easily broken down metal cyanide complexes that are considered bioavailable and potentially toxic.
That's the one regulators focus on.
Generally, yes, because it's the better indicator of potential harm to humans and wildlife. Total cyanide, on the other hand, includes very stable, tightly bound cyanide complexes like iron cyanides that are essentially non-toxic. So just measuring total cyanide doesn't give you a useful picture of the actual toxicological risk.
Got it. Wad cyanide is the key measure for toxicity. So how does the actual gold extraction process work using this dilute cyanide solution? Let's talk about the carbon and leach, or CIL, process.
Okay, CIL is very common. First, the ore is ground very finely, usually mixed with water to form a slurry. This slurry then goes into large agitated tanks. The dilute sodium cyanide solution is added, along with lime or sodium hydroxide to keep the pH high, around 10.5.
Why keep the pH so high?
That's critical for safety. At high pH, the cyanide stays dissolved in the water as the cyanide ion, CAM. If the pH drops too low, it can form highly toxic hydrogen cyanide gas, HDN, which you absolutely want to avoid. High pH also helps reduce overall cyanide consumption in the process.
Okay, safety first, so the gold dissolves. Then
As the gold dissolves, forming a gold cyanide complex in the solution, which we call the pregnant liquor, granules of activated carbon are added to the tanks.
activated carbon,
Right.
like in a water filter.
Exactly like that, but on an industrial scale. The activated carbon has a huge surface area and a strong affinity for that gold cyanide complex. The gold complex essentially sticks to the surface of the carbon granules, absorbing out of the solution. This happens progressively as the slurry moves through a series of tanks over typically about 24 to 48 hours.
So the carbon soaks up the gold.
Precisely. It's a very efficient way to concentrate the dissolved gold onto a solid material that's easy to separate from the slurry later.
And is it tricky to get right? You mentioned ore variations earlier.
Oh, it can be very complex to optimize. Different ores behave differently. Some consume more cyanide, some leach faster or slower. Modern plants use sophisticated control systems. They often blend ores, continuously monitor things like pH, cyanide concentration, and dissolved oxygen, and make adjustments on the fly to maximize gold recovery efficiently and safely.
Okay, so the carbon is now loaded with gold. How do you get the gold off the carbon?
The loaded carbon is separated from the waste slurry, the tailings. First, it's usually washed with a weak acid to remove things like calcium carbonate that might have built up. Then comes the elution, or stripping stage. The carbon goes into a special column where a hot, caustic cyanide solution is passed through it. This stronger solution reverses the absorption process, stripping the gold back into a highly concentrated solution.
So now you have a rich gold solution.
Exactly, a very pregnant solution. This solution then goes to electrowinning.
Electrowinning. Sounds like electrorefining for copper.
Similar principle. Electric current is passed through the rich solution. The gold, and any silver that was also dissolved, plates out onto cathodes, usually made of steel wool or mesh. This forms a metal sludge on the cathodes.
A sludge, and that's the gold.
That's the gold and silver, yes. This sludge is periodically removed from the cathodes, filtered, dried in an oven.
And then, the final step.
Then comes the moment of truth. The dried sludge is mixed with fluxes and smelted in a furnace, typically inside a high-security gold room. It's only after this smelting step that the gold finally appears in its familiar metallic form. It's poured into molds to create gold-silver doré bars.
Doré bars, not pure gold yet.
Not quite. Doré means they're mostly gold and silver, maybe with small amounts of other metals. These bars are then securely transported off-site to a specialized refinery for final separation and purification into high-purity gold and silver.
What a journey. From rock to solution to carbon, back to solution, then sludge, and finally a bar of metal. But what about the leftover stuff? The tailing slurry that the carbon was separated from? It still has cyanide in it, right?
Yes, absolutely. The tailings leaving the leach circuit contain residual-free cyanide and those metal cyanide complexes. And this solution must be treated to destroy or remove the cyanide before the tailings can be safely stored long-term in a tailings storage facility.
How is that detoxification done?
There are several established methods. One is natural degradation. Sunlight, air, and microbial action can break down cyanide over time. Dilution is sometimes used where appropriate. More actively, chemical oxidation processes are very common, using reagents like sulfur dioxide and air, the INCO process, or hydrogen peroxide to break the cyanide down into less harmful substances. In some cases, there are even processes to recover and reuse the cyanide.
Natural degradation sounds simple, but I imagine it has limits.
It does. While it can be effective, especially in sunny, arid climates, relying solely on it is often insufficient and carries risks. You need very long residence times in the tailings pond. There's a risk of wildlife, especially birds, being poisoned if they drink the water. And there's always the potential for overflows during extreme weather before degradation is complete. So active treatment is usually required.
And what about cyanide getting into groundwater? Is that a concern?
It is a significant concern. While cyanide breaks down relatively quickly in surface water exposed to sunlight, it can persist for much longer periods, potentially many years, in groundwater where there's no sunlight and less oxygen.
Which brings us to that striking example from Montana.
Yes, case 7.6 in the sources is quite telling. Montana remains the only U.S. state to have banned cyanide heap leaching for new lines.
And the reasons were?
According to the case study, the ban stemmed from concerns over private property rights instances where wells on adjacent properties became contaminated. Also, the potential for huge taxpayer costs for long-term, sometimes perpetual, water treatment and reclamation at some sites where containment failed. The case notes a history of cyanide releases from line facilities in Montana, often due to liner issues or operational problems, leading to contamination of water resources. It really underscores the critical importance of containment integrity and long-term water management.
And real-world spills, unfortunately, do happen sometimes.
Yeah.
How do environmental conditions affect the impact?
That's highlighted very clearly in Case 7.7, which compares two major cyanide spills. The Pyrometallurgical spill in Romania in 2000 was devastating.
I remember hearing about that one.
A huge volume of cyanide solution spilled into river systems in winter. The cold temperatures slowed natural degradation, ice cover blocked sunlight, and low river flows meant less dilution. The result was massive fish kills extending far downstream.
And the other spill?
The Omai gold mine spill in Guyana in 1995. Also a large spill. But the environmental impact, while serious, was reported as more localized. Why? Likely due to warmer temperatures, more sunlight, and greater dilution in the river system, allowing for faster natural breakdown of the cyanide. It shows how site-specific factors dramatically influence the consequences of an accident.
These incidents obviously shape public perception quite strongly.
Immensely. Even though the industry points to a long track record of generally safe operation, high-profile accidents like Pyrometallurgical understandably erode public trust and fuel opposition to cyanide use.
It highlights the need for transparency and strong performance.
Absolutely. Which leads to industry initiatives like the International Cyanide Management Code.
Right, you mentioned that. A voluntary code.
Yes, launched back in 2005 by mining companies and cyanide producers. It sets out detailed best practices for managing cyanide safely throughout its entire life cycle: transport, storage, use, and disposal.
And companies get certified.
Yes, signatories have to undergo rigorous audits by independent third parties every 3 years to verify they're complying with the code's principles. And those audit results are made public. It's a mechanism to promote responsible practices and build stakeholder confidence through transparency.
Okay, so whether it's pyrometallurgy or hydrometallurgy, managing the environmental side requires knowing what's actually being released. How do companies figure that out? How are emissions actually estimated?
Good question. Measuring and quantifying emissions is essential for management and reporting. There are basically 4 common techniques used.
4 ways. Okay.
First is direct measurement. You literally put monitors on stacks or sample discharge streams. It's usually the most accurate for specific sources, but it can be expensive, especially for continuously monitoring many points or retrofitting older plants.
Makes sense. What else?
Second is mass balance. This is more of an accounting approach. You carefully track all the material coming into a process, the sulfur in the ore, for example, and all the material leaving in products or captured waste streams. Whatever is unaccounted for is assumed to be the emission.
Sounds logical, but may be prone to small errors adding up.
It can be, especially for substances present in small concentrations or complex processes with many streams. It relies heavily on accurate sampling and analysis.
Okay, method 3.
Engineering calculations. These use established physical and chemical principles, reaction kinetics, thermodynamics, and knowledge of the specific process equipment and operating conditions to predict emission rates. Their accuracy can vary depending on how well the process is understood and modeled.
So, based on theory and design.
Right. And the fourth method is using emission factors. These are average emission rates developed from measurements taken across many similar operations within an industry sector. They're often expressed as, say, kilograms of pollutant emitted per ton of product.
Like an industry average.
Exactly. They're useful for making initial estimates, for national inventories, or when direct measurement isn't feasible, but they might not accurately reflect the performance of a specific, controlled, modern plant.
So each method has its place, its strengths and weaknesses.
Precisely. Often a combination of these techniques is used to build a comprehensive picture of a facility's environmental footprint, which is crucial for effective management and driving continuous improvement.
We have certainly covered a lot of ground today. It's been a real deep dive, from the ancient feel of pyrometallurgy, wrestling copper from rock with fire, to the intricate chemistry of hydrometallurgy, coaxing out microscopic gold. We've seen the incredible scale of these operations, the clever engineering, but also the really significant environmental responsibilities that come with digging up the metals that, well, build our entire modern world.
And what stands out is that constant interplay, that balancing act between maximizing the efficiency of metal recovery and minimizing the environmental footprint. The industry is constantly innovating better emission controls, more water recycling, finding ways to reuse waste like slag, developing more efficient leaching processes. It's all moving towards being more sustainable, trying to turn potential liabilities into assets where possible.
Yeah, that journey from rock to refined metal really hammers home how linked our industries are to the planet's resources and systems, and how human ingenuity keeps tackling these immense challenges. So here's a final thought for you, our listeners, to maybe chew on. We talked about slag and how defining it as waste versus a resource can be based as much on perception or regulation as on science. It makes you wonder, doesn't it? What other things currently labeled as waste in mining or other industries might actually hold untapped value if we just looked at them differently or developed the right technology? Are we overlooking potential resources right under our noses? Definitely something to think about. Thank you for joining us on this deep dive today. We hope you're walking away with a bit more curiosity and a much deeper appreciation for the complex, often hidden world that literally underpins our modern lives.